Okay, so I just handed out copies of last year's exam paper. So I thought that would be a good thing to do today to look at some of those past exam questions. And but so I'll go through some of these questions. But if any questions occur to you, any requests for clarification, anything like that, please do feel free to chip in and ask any questions as we go along. So as I hope you're familiar with, the structure of the exam is there's section A and section B. Half the stuff's from me, half the stuff's from Stephen, but we're a little bit flexible in what in what kind of selection of questions you answer. So there's two compulsory questions. The first question here is all from me, for kind of small, shortish parts from me. Question 2 is 4 shortish parts from Bart. Yeah, shortish parts from Stephen. And then the section B questions is 3 questions from my half of the material, 3 questions from Stephen. And in the exam, you have to do both of the questions in section A and then any 3 from section B. If you do answer more, we'll mark them all and give you your best combination marks, subject to the sectioning requirements that we have to count questions 1 and 2. Okay. So typically what I've done in previous years is to make question 1 kind of range across all parts of the unit, my half of the unit, and then questions 3 and 4 and 5, if you look at it, it tends to be 3 is about the multivariable calculus. Question 4 seems to always be about Laplace transforms, and question 5 and Fourier series. Okay, so shall I commence with question 1, looking at some of the parts of that? Is that okay? Anybody got strong feelings on that? I think I should start on another question step. Yeah, no strong feelings. Okay, so you've all got it there in fairly small print, unfortunately, but. Are we recording? Okay. I need a question. So, question 1A kicks us straight off into partial differentiation. You're presented with a function here, which is not a trivial function by any means. An exponential e to the minus y times the sine of x times y. So x and y are kind of non-trivially mixed up together there. And the question is, show how to obtain the partial derivatives, and there's 4 listed there. 2 first-order ones, the second-order one, d2f dx squared, and the mixed second-order one, d2f dx dy. Using the principles of partial differentiation and standard differentiation results. Okay. So this is a question for you to just demonstrate your basic understanding of the partial differentiation operation. Okay. I mean, I would kick off into this with a comment saying when differentiating with respect to x or respectively y, we treat the other variable y, or respectively x, if we're differentiating with respect to y, treat the other variable as a constant, yeah, as a constant, and apply the usual, the various single variable. Because once we got that comment in, the function that was a function of 2 variables, once you're regarding one of the variables as a constant, it then really becomes a function of a single variable. Then apply the various single variable differentiation results. Such as linearity, product rule, etc. I think it's no harm just giving a quick introduction like that. That goes a long way to demonstrating the person's understanding of what the calculations we're we're going to see. So we've indicated that when you're differentiating with respect to one variable, you're treating the other one as a constant and apply the various single variable differentiation results that we have. Okay. Absolutely have to do that. You can do the same job by making some short appropriate comments through the calculations as such. But that's how I like to present my stuff. So the derivative df dx, well, let's apply that. Technique. So we're differentiating with respect to x. We're treating y as a constant. So really what we see is just the sine of something times x, or something times the sine of something times x. So the derivative of sine is cosine. So we're going to have the same constant factor here times the cosine of the same argument x times y. And then think of, is there anything needed from the chain rule? And yes, there is, because it's not sine of just x. If it was just x, it would be cosine of just x, but it's a non-trivial function of x. It's this constant y times x. So applying the chain rule, we then need to multiply that by the derivative of the inner argument, which is just that constant y. Yeah. Okay. And just maybe just indicate note application of chain rule. Chain rule to sine of xy. Okay, we've described the general procedure in the paragraph above. We've indicated the chain rule there. And so that's df dx, df dy. Similarly, you look at it, but now when we look at the thing as about to differentiate with respect to y, we see something different because we see two non-trivial functions of y. Okay, the exponential function multiplied by the sine function. So thinking of this paragraph here, treating x as a constant, so we're seeing the single variable function of y, but it's a product of two component functions, the exponential and the sine. So we need to use the product rule. Okay. So we need to apply the product rule. So it's going to be, let's hold the exponential the same, differentiate the sine, so it's going to be cosine x times y times x this time, applying the chain rule there. Then we're going to add sine of xy, this time multiplied by the derivative of the exponential, which would be minus e to the minus y. And just indicate there, no use of product rule. Product rule and chain rule as before. I mean, you might want to tidy that up, maybe. Maybe we could tidy that up, take out the exponential, e to the minus y to x times cosine xy minus sine of xy. Maybe just factorizing it, cleaning it up a little bit. So how are we doing? Right, it's still two more to do. Okay, so what it's, what you want to indicate clearly here is that when you're taking a second derivative with respect to x, just there's no harm in putting in here, just indicate your understanding there that a second derivative is the first derivative of first derivative, so it's pdx of df dx. So we'll take our thing here, differentiate it again with respect to x. Again, all the y's are just treated as constants, so we do still just see y e to the minus y. And cosine this time differentiates to minus sine. The minus in front, and I've got minus sine of x times y. I get another factor of y down there, but since I've already got it here, I'll just add a square. Okay. I'm going to choose not to bother referencing chain rule again. I've already indicated that above. The crucial thing here in passing to the second order derivative is to indicate your understanding of the definition of the higher order derivatives. Did I do that right? Cosine goes minus sine xy. Yeah, it's okay. And last one is a mixed second order one, d2f dx dy. And just, similar principle. This time it's d dx of df dy. And that is honoring the way the notation is set up, because these differentiation things are operators. They're operators that apply to the function. So the operation that's indicated here is composition of the operators, differentiating first with respect to y and then with respect to x. Okay. So at least the way I've written it out there honors that order of the composition. Of course, by Fubini's theorem, we have that it doesn't really make a difference in what order you do it, as long as the function f isn't too pathological. There are examples of strange functions where it is sensitive to the order in which you differentiate them. But for most familiar continuous functions, it's always going to be the same. So d dx of df dy now, okay, that looks a bit more awkward to do because we're going to have to do product rule. Product rule, won't we? I was just going to look, would it be easier to do d dy of df dx, but then that's kind of like a triple product in terms of y, so it wouldn't really be any easier. So just got to bite the bullet and do d dx of df dy. So we need product rule on this first one. So it's going to be e to the minus y cosine of xy times the derivative of x, which is just 1. Then plus x e to the minus y times the derivative of cosine of xy, which would be minus sine of xy y, so differentiating with respect to x. So that's applying the product rule to the first term. Differentiate the next one with respect to x. That's not too bad. Oh, I should have been using that. I should have been using that form there, maybe. Yeah, I probably should have been using that form, but sorry, I was working off this intermediate expression here. So now I'm differentiating this with respect to x. So it's going to be minus e to the minus y cosine xy and another factor of y. So sorry, I started working off that middle expression. It probably would have been tidier to work off that one there. No harm. The only thing then to do might be to tidy it up by taking out any common factors you can see. The only common factor that's in all of them is the e to the minus y again. And that would leave me with cosine of xy minus x times minus xy times the sine of xy minus y times the cosine of xy. I guess you could factorize out the cosine xy there out of those two terms and write it as y plus 1 or 1 minus y times the cosine of xy, but I think we've done that enough. Tidied it up a bit. So I think that pretty much answers that question. Yeah, just to save myself a little bit of time, I just mentioned chain rule and product rule a bit at the start. But once I went to the higher order ones, I've already talked about that. So as long as I do it correctly, I wouldn't be taking off any marks. But I did take the time to indicate my understanding of what the higher order derivatives are. Okay. Any mistake? Have I captured all my signs correct? Okay. Any related query just coming off of that? Anything that occurs to you you'd like to ask about? Okay. So question 1b is a path integral. Evaluate a following path integral. It's integral of a linear differential form, so something dx plus something dy. Some things being polynomial functions in x and y. Integrate that along a straight line from the origin to a point with coordinates, given coordinates. Okay. So let's see what we have to do to carry out question B, part B. No harm, just plotting the location of our point. Just helps us to think about it. It's the point minus 2, 3. It's going to be here, 2, 3. So it's going to be this point here, minus 2, 3. Whether or not we need the sketch, yeah, we probably do. So the path is a straight line from the origin to that point. So our path is just this straight line. Okay. And the integral I, so this is our straight line C. Our integral I is the integral along C of x squared plus 2y plus 1 multiplied by the differential dx plus x squared plus y multiplied by the differential dy. Okay, so in order to carry this out, we need a description of the kind of a parameterized description of the curve, and we're going to translate the integral into effectively a single variable integral. Okay? So we parameterize the curve C, translate I into effectively a single variable integral. There's no harm getting these little introductions. They help to demonstrate your understanding, and it makes for some easier to read mathematics. So before you kind of deliver an avalanche of equations to someone, if you can, just tell them what they're going to see, and things to look out for. Okay, so what's going on with C? So said I'm going to parameterize C, so the reader will understand what I'm writing here. So, well, you see, so C is a straight line, so it's going to have an equation of some kind of form. Y equals something times x plus something. It's through the origin, so there won't be an intercept. So the constant term in the equation of the line would be 0. So what kind of line is it? It's got negative slope, and the slope is the y difference divided by the x difference. So slope minus 3 over 2. So if y equals minus 3 over 2x. Okay, so that's the equation of our line. Okay, that's good. By writing down the equation of the line, it's kind of suggesting to us that we should translate the integral I into the variable y, because it's indicating a substitution for y. So we'll stick with that theme. We'll try and translate everything into x, I guess. So that's the equation of the line. Of the line C. That's going to imply an associated relationship between the differentials. We get by taking the differential of both sides. dy is going to be minus 3 over 2 dx. And lastly, just indicate the direction and the range of the parameters. So if we're going to describe it in terms of x, so on C, let's get the range of values for x. So x begins at 0 and then proceeds to minus 2. Okay, so we're specifying the domain of the variable x there and the direction of travel. So starting at 0 and descending to minus 2 is consistent with the direction going from the origin to the point. Okay. If we had it going from minus 2 up to 0, that would be the curve going from the point to the origin, which would give you, if you did the integral that way, it would give you the negative of what we're supposed to have. Y. Okay. You might lose a mark or two if you didn't respect the specified direction. Okay, so that's the parameterization of the curve. So let's do the translation now of the integral. So I is going to become the integral now from 0 to minus 2. And we just translate everything into x. So x squared is already an x, that's fine. X squared, 2y is minus 3x. 1 is still 1. So leave that alone. Plus 1, then you got your x squared. So we'll put that there. Yeah, x squared, leave that there. The y becomes minus 3 over 2x. And with these parts, see, now we have the differential dx. These parts at the front were already multiplied by the differential dx. These parts in the bracket here were multiplied by the differential dy. So those parts need an extra factor of minus 3 over 2 multiplying that bracket. If I can put that up here, say minus 3 over 2 times that bracket. And then everything is with respect to the variable x. So maybe just before we actually do the integration, we'll just convert that integral into standard, or just convert the integrand into standard form. Bit of a messy polynomial at the moment, so let's just collect it together. So x squared, so we got 1 minus 3 over 2, so it's minus a half x squared. And you got minus 3x plus 3 over 2x. Minus 3, so minus 3 is minus 6 halves, so minus 6 halves plus 3 halves is minus 3 halves. Minus 3 over 2. Oh no, wait. Minus 9 over 4, indeed. So minus 3 is minus 12 over 4. Minus 12 plus 9, minus 3. Minus 3 over 4, is that correct? X. And then not forgetting r plus 1. Okay, so we said what we were going to do. We parameterized the curve. We translated the integral. Now it's just a one variable integral. We can just go ahead and do it. Yeah. Integral minus a half x squared is minus 1 over 6 x cubed. Minus 3 over 4x is minus 3 over 8 x squared. And 1 goes to x. And it's 0 minus 2. I mean, this now is just first year stuff, isn't it? So it's well, it'll be nothing when you evaluate it at 0, it won't be anything since everything's got an x in it. So evaluate it at the minus 2, we get minus 1/6 times minus 8, and minus 3/8 times 4, minus 2. And that's something. What it is. Four over 3, minus 3 over 2, minus 2. So that's some number of sixths. 8 minus 6 of them, minus 12 of them. Minus 10 over 6, minus 5 over 3. Yeah. So it's minus 21. 8 minus 21 is, oh my God, minus 13. Minus 13 over 6. Sounds better? Yeah. Thank you. I might, if you had everything else there, I'd probably forget that at the end. Especially if I was marking my own room. Okay. Okay for everybody? Is that, any associated questions? Does that spark any questions in your mind about anything related? These are curve integrals, path integrals. We did other examples where the path, was maybe piecewise linear, different lines. So you'd split up the integral along the first bit plus the integral along the next bit as appropriate. Then we had a more advanced thing, which I think features in one of the later questions on Green's theorem, which was relating integrals around closed paths to double integrals over the areas enclosed by those paths. Okay, so some more advanced stuff about related to path integrals and double integrals later on. Okay. So question C then parentheses, use the table of transforms to obtain the Laplace transform of the function t squared cosine t. Okay. So this is somewhat of a shorter question, I think. The Laplace transform of g of t is the Laplace transform of t squared cosine t. So we're remembering back a few weeks now. So you will in the exam be armed with your table of Laplace transforms from the formula handbook. So you'd open that up and you're wanting, I mean, the instruction is to use the table of transforms, so we ought to. We're looking for this function, t squared cosine t. So our first instinct is to look on the first page, look down the side here, and look for that function. But of course you don't see it. See something tantalizingly close? The transform of t cosine omega t. So that's nearly it, except it's a t squared in our. And then you remember there are some other things. Okay, some more associated, more general properties of the Laplace transform. And our eyes drawn to this one here. Okay, that entry there, which is telling us that if we know what the Laplace transform of f is, if we know what, so f bar here is the transform of f, if that's available to us, then we can use this property to take the Laplace transform of t times f of t. The Laplace transform of t times f of t is the negative derivative with respect to this new variable s of the transform of the original f function. So we can use that, okay? Because we've just seen on the table of Laplace transforms the result for transforming t cosine t, and we can use it in combination with that property there. Okay. So hopefully that makes sense, or I'll spell it out now in the solution. So we want to rephrase our t squared cosine of t, and it helps to write it out like this as t times t cosine of t. Okay. So we'll make a note here, preparing to use the property. And, you know, what's the harm in just repeating the property here? The Laplace transform of t f of t is minus dds f bar of s. Okay, so we've actually stated the property we're going to use there. So I've just separated off one of the factors of t, just so I see. I mean, you could do it in your head or do it in one step, just jump straight to the conclusion, but better to proceed cautiously. So if we're going to use this property, well, let's use it. It's minus dds. Of what? Of f bar s, which is the Laplace transform of the f bit. So for us, it's the Laplace transform of what's in the bracket here. T times the cosine of t. So that we read off the table. So with omega equals 1, this is s squared minus 1. All over s squared plus 1 squared. Yep. Okay. Don't think that, I mean, you can factorize the top as s plus 1 times s minus 1. Not really going to make it any simpler. So, I mean, I think we've captured most of the marks there, but probably just demonstrate again that you can do differentiation. So what's required here is something like the quotient rule. And this is a negative sign at the front. There's the square of the denominator, so that'll go up to the power of 4. And then what is it? The denominator times the derivative of the numerator. So it's s squared plus 1 all squared times the derivative of s squared minus 1, which is 2 times s. And then it's minus the numerator times the derivative of the denominator. And the derivative of the denominator, you can use chain rule. You don't need to expand it out. So chain rule is going to be 2 times s squared plus 1, and multiplied by the derivative of the inner thing is going to be 2 times s. I think if you got something like that, I'd award full marks. But you know, if you cared, you could tidy it up a bit at the end. There was a common factor there of 2 times s squared plus 1. So 2 times s squared plus 1, and that's multiplying in 2 times s squared plus 1. That's multiplying s squared plus 1 minus, that's it there, and I'll take out the 2s, so minus 2 times s squared minus 1, I believe.
Could you not take a factor of s squared plus 1 from top and bottom?
You could indeed. Thank you. Yeah, so there's further simplification there. What's going on inside this square bracket first is going to be s squared minus 2s squared, so it's going to be minus s squared and 1 plus 2, 3, I believe. And yeah, so minus 2s, and not s squared plus 1 will reduce the denominator to cube. About as simple as you can get. There's too many minus signs there, maybe. S squared minus 3 over s squared plus 1. Okay, the crucial stuff there is the stuff about the Laplace transform. That's really what I'm interested in assessing here. Whether you're aware of these properties and able to implement them in a not too complicated case like that. So yeah, maybe just a little comment here using transform from the table here. I mean, it's pretty clear that's what you're doing. No harm to indicate what's going on. Okay. So then there's a part D. Now, if you don't mind, here right now, I think I'm going to skip this part D because we did cover it quite recently in the Fourier series lectures. I'd rather maybe do one more part, which is something less recent that we benefit more from here. So for part D, I'll just refer you to the recent lectures. And we can make better use of our time by looking at something else. So there's question 3. There's a question about the Jacobian of the Cartesian coordinate system, the transformation to it from Cartesian coordinates. There's a double integral changing the order of part B. There's finding stationary points in part C. 4 all on Laplace transforms, 5 on Fourier series. Shall we go for one of the parts of question 3? Why not? Most appropriate for a revision session. So looking at question 3, okay, well let's go for 2 part A, I guess. So they tell us that the equations relating the Cartesian coordinate system x, y, z to the cylindrical polar coordinate system are those equations given. X equals rho cosine theta, y equals rho sine theta. Use these to find the Jacobian determinant of the transformation from Cartesian coordinates to the cylindrical polar coordinates. Okay, so it's asking about the Jacobian determinant, so we better define what that is. So we'll say the Jacobian determinant, and it's notated as the rho theta z over dx y z. So that's how it's written. So the Jacobian determinant this of the transformation from Cartesian to cylindrical is the determinant. So it's a determinant, so it's obviously one of these. So it's this determinant. So it's a 3x3 determinant. I keep feeling I'm doing something weird here. Just bear with me a moment.
Does it not have X, Y, Z? If it's going X, Y, Z to rho theta Z.
That's my nagging feeling.
Is it not the other way up?
Yeah, it is the other way around. You saw me pausing there. I was, yeah. Sorry about that. So, as Libby reminded us there, we got to flip those. Okay, so it's actually the reciprocal of that thing. Okay. So, yeah, so we're talking about d x, y, z, d rho theta z. Okay, so it's this, yeah. That's what I was getting worried about. So it's this 3x3 determinant. We've got old variables, we've got new variables. Brains all over the place. Yeah, so the old variables are indexing the rows. Excuse the pun. And the new variables are indexing the columns. So we have a row column. So we have a dx d row, dy d row, and a dz d row. Then we got a theta column, dx d theta, dy d theta, z d theta. Then we got a z column, dx dz, dy dz, dz dz. Okay, so we've got rows in the matrix and the Greek letter rho, so you got to be aware of that. Okay, so you get the definition down. So now you work from the transformation equations given in the question to put down each of these partial derivatives. So dx d rho is cosine theta. Dx d theta is minus rho sine theta. Dx dz, and you look at the thing, you don't see any z's and x because it doesn't depend on z. You increase the height of the point, it retains the same rho and theta coordinates. So dx dz is 0. dy d rho, sine theta, dy d theta is rho cosine theta. dy dz is 0 again, there's no z's and y. dz d rho and dz d theta are 0. There's no rho or theta in z. And lastly, dz dz is simply 1. Okay, so just obtaining partial derivatives here. Obtaining partial derivatives from the equation is given. So we end up with this, this determinant. Do various things here. You can first, there's a common factor you can take out, because that middle column has a common factor of rho in it. See rho, rho, and there's also a rho here being multiplied by 0 to give you 0. So you can take that factor rho out. It's rho into cosine theta minus sine theta 0. Sine theta, cosine theta 0, 0, 0, 1. Okay, so we can take factors out of our determinant. Remember using those properties in Stephen's coursework question, simplifying a determinant. Then we can go for expansion of the determinant. You clearly want to expand it along the third row or down the third column because it's 0. There's no cofactors to work out. There's just a cofactor for this position, which is going to be the upper 2 by 2 determinant. This is going to be rho times this 2 by 2 determinant. I'll just indicate factoring there, factoring the second column. Here, expanding along third row, ROW, RHO. And then this 2 by 2 determinant is our old familiar cosine theta plus sine squared theta. So it's rho. So this quantity rho is the Jacobian determinant of the transformation from Cartesian coordinates into cylindrical polar coordinates. These Jacobian determinants, well, the use we saw of them anyway is when we're translating in double integrals or volume integrals in general from one coordinate system into another. This Jacobian determinant occurred as it's essentially the volume multiplier. It describes how the volume or the area or the volume, depending on the dimension, the area element to the volume element, how it scales when you look at changes in the new variables. Okay. Okay, I might just pause there for now. Oh, pause. Yeah. So I'll be seeing some of you in a tutorial tomorrow. We'll keep looking at these things. When we return after Easter, I'll have 2 lectures with you on the Monday, so we'll do further these kinds of revision. You can send me queries over the break by email. You're welcome to. I'll respond accordingly. Do make use of all the past papers and solutions on Moodle, but also, look back over all the tutorial questions as well. Don't just exclusively focus on the past papers, because you might miss something out. Okay. Okay then. Thanks for your attention. Enjoy the break. If I don't see you before then.